Okay, next topic is work integrals. Okay, I want to talk about this R2 vector field. Really easy field, right? It's everything's moving in the northeast direction, 1, 1, 1, 1. Wherever we are, nice constant vector field. And I want to talk about some paths through this vector field. So I'm going to share this. Well, actually, before I do that, we are in the work integrals section page, and there's some nice images that we're going to work from. So you've got your journals, and I'm going to put up versions of this in CalPlot 3D. All right, so this is our field. We went in, entered M and N are 1, 1. We restricted the view to 2D. It's a 2D field, so we have the blue vectors. And now what I've added in red is a plane curve. R of t, that's the one here in red, is just TT. So just this line straight through. And this line happens, it's very easy to see the way the field is plotted and the way the plane curve is plotted, that if this was point A down here, and this was point B up here, we're moving in this direction. And I guess I can add orientation errors to this guy. Okay, so those red arrows, that's the movement, the direction of flow. It's easy again to see, to go from the lower point A to the upper point B, that we are moving with the vector field. And so the amount of work done by the field then is going to be positive because we're moving with the field. On the other hand, if I were to reverse the orientation, which is this, oops, not that one, this. So let's see, let me see if I can do this one. Okay, so just negating the t's in both cases. Now we're going in the other direction. If this is A, I'm sorry, this is A and this is B. So we're actually having to move against the flow of the field to make progress. Then in that case, the work is negative because we're moving against the field. Let's put it back to the original orientation. Okay, so with the field, when you're moving with the field, you'll have positive work because work is force times displacement. And so that is what it is measuring. We're moving with it. If you're moving against it, which would be completely opposite, you have negative work. And then on the other hand, turn that one off. Let's put on this one that moves perpendicular. Every time we move along this purple one, if A is down here, B is up here, or even vice versa, we are always moving orthogonal to the direction of the field. And in that case, the work is 0 when you're moving orthogonal to the field. And we're going to get to an exact definition a little bit in the next couple of videos. Right now, we're trying to build up intuition. We will be able to precisely quantify how much work is done by the field to move a particle from here to here. Well, in this case, the field can't do it. The field can't move the particle. This would have to be, if this blue is river flow with the current at the top of a river, and there's a fish trying to swim up top, the fish is doing all the work to go from A down here to B over here. Nothing, he's getting no help from the field. So the field contributes 0. Now, this third one I want to show, here's a plane curve in green. This plane curve, let's say we started down here at very similar to the, well, I'm going to put the one in red in, right here, the intersection of those, and we wanted to, in the red one, we said we have positive work. The field is pushing the fish or the leaf or the particle through the field, and so there's positive work. In the green, sometimes it starts off orthogonal, right? The green line is orthogonal to the vectors in the field, and then it starts to move with them. Mostly, still mostly, maybe 45-degree angles there. So the field is doing some work, none along here, a little bit here, a little less. So not quite as much work done by the field to move the green from A to B as opposed to the red from A to B. The field is doing more. So you're just measuring, in this case, you're estimating the work done by how much those blue vectors in the field match up with the path shown. And so you have a couple Yeah, then, so let me stop the screen share. You have a couple activities in this section. So we're just trying to, for work intervals, again, we're going to be able to compute the exact amount of work done. For now, we just want to get a sense of approximately how much work is done. Is it positive? Is it negative? Is it zero? Is it about zero? Is it more for this path than that path? And so you have a couple estimating the work done activities here in your journals that you're going to go through. But you want to use that idea that is the path from A to B, and again, the path will be directed and that will matter. Look at the path from A to B. Is it mostly, you can even think about it as its tangent vectors at any point along that path. Are those tangent vectors moving with the field? Then you have positive work. Against the field, negative work. Orthogonal to the field, zero work. And you want to sort of sum that along the whole path, right? So there's some path through the field, and every point on that path, you could stop and take a tangent vector, tangent vector, tangent vector, tangent vector, and do those tangent vectors line up with the vectors in the field? If they largely do, as you're summing through the path, you'll have positive work done by the field to move a particle from A to B. Okay, so that's the first part, and then the next video we'll quantify that.